Circle S has a center hk and radius r. The equations of S1 and S2 are as follows. S1 is x squared plus y squared minus 9 equals 0. S2 is x squared plus y squared minus 6y plus 8 equals 0. Show that 6k equals 17 plus 4r. So this equation gives a relation between k, the y value of the center of circle S, and the radius of circle S. Now S1 and S2 are fully specified circles. S isn't. S happens to touch both of these circles. We could show S in a different position. We could show it here. As long as it just touches S1 and S2 at one point, we have basically an infinite number of possibilities for circle S. So circle S is certainly not fully specified. However, we do know that since S touches S1 externally, that means at one point, the distance between the centers of the two circles is equal to the sum of the radii of the two circles. The line joining the centers of these two circles passes through the point of contact of the two circles. Let's get the center and radius of circle S1. We can actually write circle S1 like this. We can bring the minus sign over, and you might recognize this form. A circle that has this form, that is a form x squared plus y squared equals r squared, is a circle that's centered at the origin, 0, 0, and has a radius equal to the square root of 9, which is 3. So that's the easiest way to get the center and radius of this circle. Of course, we could do it the more long-winded way, and this is the way we have to do it for many circles. Compare it to the general form of the equation of a circle. So this is the fully expanded form. Since there's no x or y term in this equation, we write 0x and 0y. The coefficient of x is minus 2h. So minus 2h equals 0, and from that we get h equals 0. Similarly here, minus 2k, the coefficient of y equals 0. So we get k equals 0. To find the radius, we use a formula, root h squared plus k squared minus c, where c is the constant in the equation. The constant is minus 9. So here we get h is 0, k is 0, c is minus 9. So we minus 9, that's plus 9. So we get 3. Of course, it's much easier to do it this way, but I'm just showing what we have to do in general. So the distance between the centers of these circles is r plus 3. And we can get that distance another way. We have the coordinates of the two endpoints, so we can just use the distance formula, get the square root of the difference in the x values squared plus the difference in the y values squared. So we take h minus 0 and square it, then we take k minus 0 and square it, and this simplifies to root h squared plus k squared. So you can see here we have an equation connecting r, h and k, but we want to prove something that just connects k and r, so we have to use the other information that's given. So we're given that S touches this circle S2, which means that the line joining the centers of circles S and S2 passes through the point of contact of the two circles, and the distance between these two centers equals the sum of the radii. Now we know the distance from here to here is the radius of S, which is r. Same as here, of course. We need the radius of S2 now. So here is S2. Now I've written in 0x for the x term. You can see there's no x term in it. So I want to show this equation in its full form. X squared term, y squared term, x term, y term, and a constant. So we can compare it to the general equation of a circle and find h and k. So comparing here, you see that minus 2h equals 0, and from that we can get h. H then, if minus 2h is 0, then h is obviously 0. 0 divided by minus 2. And the coefficients of y have to be the same. Minus 2k is minus 6, so k is half the coefficient of y with the sign changed. So we get plus 3. Next we want the radius of the circle, so we use this formula here. H is 0, k is 3, c for this equation is plus 8, so we've minus 8. So we get root 9 minus 8, root 1, which is 1. So now we have the radius of S2, this distance here is 1. So the distance between the centres of circles S and S2 is R plus 1. And that distance is equal to the distance between the point 0, 3 and HK, so we can use the distance formula. This essentially comes from Pythagoras' theorem. We get the difference in the x values. So if I subtract the x values, it doesn't matter which order we do the subtraction because we're squaring here. So I have 0 minus h squared, and add on the difference in the y values, that's 3 minus k. Again, we could write in k minus 3, it won't matter. 3 minus k here, we have to square that. Now, minus h all squared is just plus h squared. Let's square this out. 3 squared is 9. We get minus 3k times 2 is minus 6k, and then we get plus k squared. Now I have to somehow combine these two equations in such a way that we get rid of this get rid of h squared, because h doesn't appear in what we're trying to show. So we have to somehow get rid of h squared. It might be a good idea to make h squared the subject of both of these equations, and then equate what we get, and we should get an equation just connecting k and r. So try to get rid of, or make what we don't want, which is h squared, the subject. So how do we get at h squared? Well, we have to square both sides of this to get at h squared. Squaring the left hand side gives r plus 3 squared. Square the right hand side gives h squared plus k squared. We do the same for this here. Now I'll make h squared the subject of this equation here. And I will also expand out r plus 3 squared. So h squared is going to be r plus 3 squared minus k squared. Squaring this out gives r squared plus 6r plus 9, and we subtract the k squared. So I've shifted the k squared over, and I've also just switched it around to put h squared on the left hand side. I'll do the same here. I'll square this out, and I'll get h squared as the subject. So if I square this out, we get r squared plus 2r plus 1, and then we shift everything else over, so we get a minus 9 plus 6k minus k squared. So basically I've just brought 9 minus 6k plus k squared over to the other side, squared this out, and then I've just turned it around so h squared appears on the left. So now we see that this thing and this thing here are equal to h squared. They're equal to the same thing, so they must be equal to each other. So we put this equal to this, and hopefully we'll deduce this. So you see, this does not involve h squared. We don't want h to appear in this. So set it equal to this. Now we see we can subtract r squared from both sides, so all the quadratic or square terms are disappearing. And I'll leave the 6k on this side because 6k appears on its own here, and I'll shift everything to the left hand side. So we're going to get 6r minus 2r. Well, that's 4r. That looks good. So we have 4r here, and minus 9 is brought over and added to plus 9 to give plus 18. I'll just write it down carefully. Bring the plus 1 over, and we're left with the 6k, and that's what we have to prove. 6k equals 4r plus 18 minus 1, that's 4r plus 17. That's good, I don't have to remake the video, it worked out. Next we want to show that 16h squared equals 5 into 2k minus 1 times 2k minus 5. So this relation here connects h squared and k. R doesn't appear in it. So what we could do is, say, take this equation here and plug in for r. So we don't want r to appear, of course. So we can use the result of the previous part, as this result incorporates all three circles. So if I rearrange this to make r the subject and plug in for r here, we'll have an equation connecting h and k only, and hopefully it will be this result here. So I'll make r the subject of this equation. So we get 6k minus 17. So subtract 17 from both sides and divide by 4. Plug this in for r and see what happens. So I've written this equation here. Okay, we need to write this as a binomial, just two terms, although we can also take out 1 over 4. I'll write 3 as 12 over 4, so we have this common denominator of 4, and we have 6k minus 17 plus 12, that's 6k minus 5 divided by 4 squared equals h squared plus k squared. Now squaring this, we square the top, 6k minus 5 squared, square root of 4 gives 16. I'll multiply both sides of this by 16, and I'll turn it around at the same time. So multiplying the right hand side by 16 gives 16h squared plus 16k squared. And I'll expand this out because at the end of the day the quadratic involving k has been factorized. So if we expand this out, 6k times 6k is 36k squared. We have minus 30k times 2, that's minus 60k, and then we have plus 25. So we want to get 16h squared on its own. 16h squared is the subject of this, so subtract 16k squared from both sides, so it's going to give 20k squared minus 60k plus 25, and hopefully this quadratic here is the same as this here. We just need to factorize this, or alternatively you could just multiply this out and see if you get this. You can see 5 is taken out here, so I've factorized 5 out of this, and we get 5 into 4k squared minus 12k plus 5. Okay, for the factors of 4 squared I'll put down 2k times 2k. For the factors of plus 5 I'll use minus 1 times minus 5, and if we check here, for the outer terms we have minus 10k, and the two inner terms give minus 2k. Put them together gives minus 12k. Now I've just been to GeoGebra to do sketch of circles S1 and S2, and they don't appear as in the picture here. This is actually what the two circles look like. These are circles S1 and S2. S1 is the large circle centered at the origin, x squared plus y squared equals 9, and here's S2. If we expand this out, we get x squared plus y squared minus 6y plus 8 equals 0. That's the form it comes up in GeoGebra. Circle S touches both circles. Now, to see where the centers of the circles that touch both of these circles lie, we can use the fact that the center of S satisfies this equation here. The x value of it is h, the y value of it is k. So what I'm going to do is plot this curve here. So I've just replaced h with x and k with y in the second relation that was proven. So if I input this, we get the locus of a point, which is the center of a circle that touches both of these circles. So a circle centered anywhere on this dotted curve can be drawn to touch both of these circles externally. So I'll pick a point on the curve. So I'll put this point onto the curve. So this point will be the center of a circle that touches both of these circles. And we know that the line from the center of this circle to, say, this circle here cuts the circle at the point of contact. And the same is true for the second circle, of course. So we need the point of intersection of these two lines with the two circles. Now we can draw the circle, centered here, passing through the 2 points. So this is what the picture in the question was meant to look like. So here's circle S. Circle S2 has radius 1. This circle here is S2, and this one here is S1. It has radius 3. The radius of S is R, and R varies, of course. Also the center HK varies. So the center of S can be anywhere on this curve, well, except where the circles overlap. Of course, I can do the same for this curve down here. Actually, for our purposes, we're only interested in this circle here. So we're basically, the center lies in this curve here. We can forget about this lower curve.